All right, welcome back to another calculus lecture. In today's lecture, what I want to talk about is a method for computing the absolute maximum and minimum values that a function can attain. So oftentimes we have reason to look at a function over maybe an interval of time and say, okay, what is the absolute maximum and the absolute minimum value that that function attains over that interval? And under very general assumptions, a function is guaranteed to have a maximum and minimum value. And in fact, that's going to be the first thing that we write down today. So theorem. So if f of x is continuous, and in fact this is the only hypothesis that we need, if it's continuous on the closed interval a to b, so I'm going to include the endpoints and demand that f of x is continuous at the endpoints, then f of x attains an absolute maximum and minimum value. Okay, so as long as I have a continuous function, no matter how crazy my function is, I can always be guaranteed that my function will have an absolute maximum and minimum. And in fact, I should have wrote this before, but this is called the extreme value theorem. It's like the usual value theorem, but it drank too much Monster. Oh, wow, my jokes are bad. Anyways, so the extreme value theorem guarantees us that we have these special points. So how do we go about finding these particular points? So that's what I want to talk about for the rest of the lecture. And the way that we do this is through something called the closed interval method. So closed interval method. And not everyone sort of calls this by the same name, but it's the same principle no matter sort of how you slice it. So to find the absolute max and min values of and we're going to demand that it is continuous on a closed interval. So of a continuous function, I should say. F of x on the interval a to b, it suffices to check, so we only have to check a finite number of points. So we have to check the two endpoints of the interval. That is x equals a and x equals b. That is, we're going to evaluate the function at those points. And b, we just need to check the critical points as well. And moreover, we don't have to check all the critical points. We just need to check the critical points of f of x that lie in this interval. So which lie in a to b. Now, it is possible to construct very sort of degenerate functions that behave very strangely, where they're continuous everywhere, but differentiable nowhere, so that every point in their domain is a critical point. But for our purposes, we're just going to have nice enough functions where this is just a finite list of things we have to check. Okay, so if I want to find the absolute maximum and absolute minimum values of a continuous function on a closed interval, it suffices to check the two endpoints of the interval and the critical points of f of x which lie in that interval. So maybe let's go ahead and do a couple of examples just to get our hands dirty with this. So example. So let's compute the absolute, and we might also call this the global maximum and minimum, absolute max and min of, and the function we'll use for this first example is just x plus cosine of x. And we're going to do this on the interval 0 to pi. Okay, so I want to compute the absolute maximum and minimum values that f of x attains on this interval using the closed interval method. So let's go ahead and just write that out. So let's just go ahead and evaluate the endpoints. F of 0 is 0 plus cosine of 0. Cosine of 0 is 1, so you can put that in on the calculator if you don't know that. And f of pi is pi plus cosine of pi. And cosine of pi is negative 1. So this is pi minus 1. Okay, so there are the two endpoints. Now we just need to compute f of x at its critical points. So first of all, we need to find the critical points. So f prime of x, to do that, we differentiate. This is a function that is defined everywhere, so, and its derivative is also defined everywhere, so we're not going to have any points where the derivative fails to be defined. So we just need to check the zeros of the derivative. So f prime of x is going to be 1, and then the derivative of cosine of x is minus sine of x. And we set that equal to 0 to find the critical points. And if I move things around, then I have that sine of x is equal to 1. Now, what values of x makes this statement true? Well, sine is equal to 1 whenever I am at pi over 2 plus or minus any multiple of 2 pi. So if I add a multiple of 2 pi, all it does is just swing me back around to the same point on the unit circle. So the only solution that this holds for that is in my interval is in fact pi over 2. So in general, sine of pi over 2 plus 2 pi times k, k being just any integer, this is equal to 1 for any integer, whole number, that is, k, but only pi over 2 lies in 0 to pi. So it's the only one that I care about. It's the only one I have to check for my closed interval method here. So we've got our one critical point that happens to be lying in our interval. Let's go ahead and evaluate the function at that critical point. So we take this value, plug it back into the original function, not the derivative. So sine of pi over 2, I'm sorry, that is not what I meant to write. F of pi over 2 is equal to pi over 2 plus cosine of pi over 2. And cosine of pi over 2 is 0. So cosine gives you the x-coordinate of your angle, and sine gives you your y-coordinate. So if the y-coordinate is 1, it means that the x-coordinate is 0. Or if you don't know this, you can just look up a unit circle or put it in on a calculator. So this is just pi over 2. And so we have 3 points that are our candidates. So candidates, it's election season, isn't it? So fitting. Candidates are x equals 0, pi over 2, and pi. And our values, let's just summarize. So f of 0 was 1, f of pi over 2 was pi over 2, and f of pi was pi minus 1. And now all I have to do is just look at these values and see, okay, of 1, pi over 2, and pi minus 1, what's the biggest and what's the smallest? Well, 1, that's easy enough, it's 1. Pi over 2 is about 1.5, so if you think about pi being close to 3, then pi over 2 is going to be about 1.5. And pi minus 1 is about 2.14, something like that. So our minimum value is 0, 1, and our maximum value is pi minus 1. So we're done. That's all we needed to show. So we just wanted to compute what are the extreme values of our function, and we did that using the closed interval method, using this very simple process. Okay, so let's maybe do another example. So compute, and I'll word it differently, the extreme values of f of x equals, I have to look at my notes, x cubed minus 9x squared plus 24x minus 7. And I want to do that on the interval 1 to 3. Okay, easy enough. So we apply the closed interval method. First thing we do, let's evaluate f of x at the endpoints of the interval. So f of 1 is equal to 1 cubed minus 9 times 1 squared plus 24 times 1 minus 7. And what is this? 1 minus 9 plus 24 minus 7, which is, this is negative 8, negative 15, and then 24 minus 15 is going to be 9, positive 9. This is the sort of thing that you can just put in on a calculator. I'm just too lazy to actually have a calculator next to me. So there's f of 1. Now let's do f of 3, a little bit more work this time. So f of 3 is 3 cubed minus 9 times 3 squared plus 24 times 3 minus 7. This is going to be 27 minus 9 times 9 is 81 plus 72 minus 7. And let's see, 72 minus 81 is negative 9. 27 minus 9 is 18, and then 18 minus 7 is 11. So hopefully I've done that correctly. Let's just double check. Yes. Okay, so there's my function evaluated at my two endpoints. Now, let's go ahead and compute the derivative. So f prime of x is 3x squared. We just apply the power rule. Minus 18x plus 24. And then the 7 just goes away. And we could use the quadratic formula to find where this is equal to 0. And this is a polynomial, so it's defined everywhere. There aren't any points where the derivative is undefined. So the only points we have to check are where the derivative is 0. And I can apply the quadratic formula, or I can just factor this. I wrote the problem, so I made sure it was factorable. So if I pull out the 3 in front, I get x squared. 18 divided by 3 is 6. And then 24 divided by 3 is 8. There we go. And this also factors, so two numbers which add to negative 6 and multiply together to give me positive 8. This is how you factor a quadratic. This is going to be 3 times x minus 2 times x minus 4. And if you don't believe me, you can take this and just expand it out to get back to this expression. Okay, so this tells me that my two zeros of my derivative are x equals 2 and x equals 4, but only x equals 2 lies in my interval. So only x equals 2 lies in 1 to 3. And so let's go ahead and evaluate the function at x equals 2. So f of 2, this is 2 cubed minus 9 times 2 squared plus 24 times 2 minus 7. And what is this? 8 minus 9 times 4 is 36 plus 48 minus 7. So this is 12 plus 8 is 20 minus 7 is 13. Okay, so now we just compare and see what's the biggest value and what's the smallest value. Well, I have f of 1 equals 9, f of 2 equals 13, and f of 3 equals 11. Well, here's my min, and here's my max. And we're done. That's it. So the closed interval method, it sort of gives us this very quick way to find these absolute maximum and minimum values. And sometimes you can have a pretty complicated function, but its derivative is easy enough to work with and find its critical points, and then you just evaluate the function at these critical points and at the endpoints, and it's all you have to do. So those are the two examples I wanted to work. I wanted to show one more example of when the closed interval method does not apply. So if I have let's see, another example. So y doesn't, there we go, my mic is hanging down a little bit. Why doesn't the closed interval method work for, oh my goodness, microphone, thank you, for f of x equals 1 over x on the interval 0 to 1. So if I were to graph f of x on the interval 0 to 1, then, okay, here's 1, here's the origin, 0. As x approaches 0 from the right, my function is going to blow up to infinity. Okay, so it doesn't have an absolute maximum on this interval. Well, why is that? So why doesn't f of x have an absolute max? Certainly has an absolute minimum. It's right there. It's 1. Absolute max on 0 to 1. And maybe if you'd like to think about it, you can pause the video and try and think about what the answer should be. But I'll go ahead and tell you it's because the function f of x is not continuous on this interval. So f of x equals 1 over x is not continuous on the interval 0 to 1. It's not continuous on a closed interval, or at least the closed interval that we're interested in. And so the extreme value theorem, which is what we're using when we do the closed interval method, that does not apply here. So the extreme value theorem doesn't apply. And so we can't use the closed interval method. And, we really shouldn't be, because we're not even dealing with a continuous function in the first place. Okay, so the closed interval method is not always applicable. You can have these instances where the function you're interested in is not continuous on the interval that you're given. But in those instances, you should be able to say why that's true or not true, and what's sort of the problem there. So in your homework, you'll have one or two questions about why does the closed interval method work here, and if it does or does not, explain why. Okay, so that's everything with this lecture. In the next lecture, we're going to use the closed interval method to attack some problems that sort of have the same flavor as related rates problems, and these are called applied optimization problems. These tend to be sort of longer problems and a little bit drawn out, and so we'll do the same sort of thing where we look at a process for solving these problems and go at it that way. All right, so see you all in the next lecture.